Well, hello. So hopefully you can see the worksheet that I have here in front, and possibly if I click onto here you can see the PowerPoint. If you have anything that you'd like me to go over in relation to this, then just send me something on the chat. Just 1 second. I'm just going to see whether the YouTube streaming is working here. And let me just put this, see if we can get this right on my computer. 1 second. And let me just... Okay, yeah, I think you can see the PowerPoint here. Now, why is the stream looking so weird? 1 second. Okay, it looks fine there. Does anybody have any questions? And let me just... Okay, yeah, I think you can see the PowerPoint here. Now, why is the stream looking so weird? Okay, that's cool. So if I look at this sheet here, it looks fine there. Let me just pick this up. Does so we've got anybody have any questions? The first part of the sheet we were just going over how to identify the PowerPoint different compounds here. Looking so weird. Okay, that's cool. What I'd like to know if I look at this sheet here, it looks fine. Let me just... Actually, this isn't... So we've got anybody have any questions? The first part of the sheet we were just going over how to identify the PowerPoint different compounds here. Okay, that's cool. What I'd like to know if I look at this sheet here, it looks fine. Let me just... Actually, this isn't... So we've got anybody have any questions? The first part of the sheet we were just going over how to identify the PowerPoint different compounds here. Okay, that's cool. What I'd like to know if I look at this sheet here, it looks fine. Let me just... Actually, this isn't... So we've got anybody have any questions? The first part of the sheet we were just going over how to identify this PowerPoint different compounds here. Okay, that's cool. The live stream has about a 10 seconds. If I look at this sheet here, it looks fine. Let me just... Actually, this isn't... So we've got anybody have any questions? The first part of the sheet we were just going over how to identify. I'm just going to start on this word. If you have any questions... Okay, that's cool. The live stream has about a 10 seconds. If I look at this sheet here, it looks fine. Then just write them in the chat, and I will... Anybody have any questions? Try and answer those. The first part of the sheet we were just going over how to identify. I'm just going to start on this word. If you have any questions... Okay, that's cool. The live stream has about a 10 seconds. If I look at this sheet here, it looks fine. Then just write them in the chat, and I will... Anybody have any questions? Try and answer those. The first part of the sheet we were just going over how to identify. I'm just going to start on this word. If you have... Okay, can you just hear one voice now? That's cool. The live stream has about a 10 teasing off. If I look at this sheet here, it looks fine. Then just write them in the chat, and I will. Anybody have any sheet here? Try and answer those. The first part of the sheet we were just going over. So this any voice has one voice. If you have, can you just hear one voice now? That's cool. The live stream has about a teasing off. If I look at this sheet here, it looks fine. Then just write them in the chat. Okay, how's that now? No, what on earth is happening there? There's still two. Weird. Okay. Oh, right. Okay, right. 1 second, I'm just... So you can hear one now? Cool. Okay, right. Does anyone have any questions? Okay, well, I'm just going to go through the sheet anyway. So this exam that I'm going to be going through is 2.4, or Achievement Standard 91164, and it's the exam where we talk about the shapes of molecules, their polarity, we talk about the types of solids, and we're also talking about the energy that, the energy of reaction. So we do calculations around that. Remember, bond energies and the energy from a reaction. Today, I'm just going to go over the types of solids, and we're going to practice some of those paragraphs. So the first thing I'm going to do, and the first thing I had on the sheet is just a quick recap. And on the sheet, the first thing I had there is a table that had the types of solids, the types of particle, and the attractive forces between particles. And on the right I've got a wee branching key, but actually in the exam you won't have the branching key. Okay, so we know that that's not going to be in the exam. We are not going to have a periodic table that has the wee staircase on it. We have to imagine that, and we need to know that the metals are on the left and the non-metals are on the right. So when we look at the very first substance here, and that's carbon dioxide. Yep. So what we notice here is that there is a carbon atom and there is an oxygen atom. So that's here and here. They are both non-metals. So we go down here and go, is it silicon dioxide or carbon? No. Is the solid made up of only metal atoms? No. Is the solid made up of metal and non-metal? No. It's only made up of non-metals, so it's going to be molecular. So I go in here and I'm going to fill in molecular. Okay, and then I'm going to say the type of particles. If I look carefully at this, this is a carbon dioxide particle, or it's going to be a carbon with two oxygens like this. So this thing here in its entirety is actually a molecule, because it's made up of discrete particles. So that's a molecule, and we need to remember that because it's a molecular solid, the types of attractions between it are weak, intermolecular, molecular. Now you have this sheet in front of you. I'll give you a chance just to do the next one. Just have a go at the next two and just see what you get from them. Look at the table on the right. From the table, write down its name, and then write down the type of particle and the attractive forces. Sorry, not the table, the branching key. So you're going to do, let's do this one, actually let's do 3. So I'm going to give you just 30 seconds. I want you to go through the table, see if you can tell me the type of solid, the type of particle involved, and then the type of attraction. And write those down on the table. I'll just have a wee break here. Remember, so for the second one, we're going to be looking calcium, carbon, oxygen, finding those on the periodic table. Are they all on the one side, or are they on different sides? And from that, we're going to work out what they are. Okay, I'm going to start writing down some answers here. So calcium is on the left hand side, it's here. Okay, so it's a metal. Calcium. Carbon is on the right hand side, it's here. And oxygen, sorry, left hand is on the right hand side. So I have atoms from the metal side and the non-metal side. So this one here is the solid is made up of metal and non-metal atoms. So it's going to be ionic. So I'm going to write here, ionic. Type of particles, because it's ionic, they're going to be ions. If we were specific, we would say they're calcium and carbonate ions, or that's CO2 plus and CO3 2 minus ions. But if you don't know the ions or the charges on them, then just write down ions. And the type of attractions are ionic bonds. So the next one we look at is one of the 2 exceptions. So we have silicon dioxide, and we actually have this one down here, carbon solid. So silicon dioxide or carbon solid are in their own special group. They're in the group of extended molecular solids, or we call them covalent network. Covalent network. Now, this one here is a wee bit different. It looks like it's a molecule, but it's not. What it actually is, and I'm just going to draw this at the top. It's silicon atoms bonded to oxygen atoms, bonded to silicon atoms, like this. Bonded to oxygen atoms, bonded to silicon atoms. So what you can see here is that actually this is a molecule that goes on in 3 dimensions in a lattice kind of forever. So it's not made up of a discrete silicon dioxide molecule. It's made up of silicon atoms and oxygen atoms. So here we would go silicon and oxygen atoms. Attractive forces between the particles. So this is a covalent network. They have covalent bonds. Let's check, see if we got the last one right. Aluminium. Where are you, aluminium? Right, just here. Yep, there it is. On the periodic table, on the right here, it is shaded in blue. It's on the left of the staircase. It is a metal, so this is going to be metallic solid, right? Now this one's interesting. It's one that people often get wrong. So you are going to write down that there are Al or metal Al atoms, because that is true. This is a regular lattice, and let me draw it here. So you're going to have all of these metal atoms. But what we also have is you have these delocalized, or C, of electrons. So those little electrons just in between. Okay. So this one here is, whenever we see a metal, we have to write down that there is the metal atom, aluminium atom in this case, and then we also have to write delocalized electrons. Okay, for this type of bond, we would actually say that this is a metallic bond. Now, we have in the past, and it's okay to write, both the ionic bond and the metallic bond are strong electrostatic attractions. That's how we would describe them if we were being specific and detailed. But actually for this task, and for any of our explanations, we just need to use these 4 different descriptors. Weakened molecular attractions for molecular solids, ionic bonds for ionic solids, covalent bonds for covalent network, metallic bonds for metallic. So if you actually get the type of solid correct, the type of bond, you're going to get quite a big hint in the type of bond that it is. I'm going to move down to the actual, I'm going to leave this free. You can catch up on that later. And I'm going to look at, we're going to start and see if we can answer this sheet here. Okay, so you know what's interesting is that you have all of your names in front of the stream, and I don't know why that's there. And let's see if I can get rid of that. How do I get rid of that? It's somewhere hiding here. Oh, I can't find it. Anyway, I'm going to see if I can fill these in. Okay, so copper, type of solid. Look to the left, we'll see that this one is metallic. Now, because it's a metallic solid, right, it's going to have atoms and the part that we often leave out, which is the delocalized electrons. Because it is metallic, it's going to have metallic bonds. The next one has, here is a metal, and these are non-metals, right? That makes this ionic. That means that they are, it's made up of ions. Well, we can say positive and negative ions. That would be a bit more descriptive. Or we can call them cations and anions. What we can do also is, we know it's ionic, so it's going to have ionic bonds. These are strong ionic bonds, strong metallic bonds. Carbon dioxide, 2 non-metals. So this is going to be molecular. Anything that is molecular is made up of discrete molecules. That means molecules that are independent, but we can just write down molecules. Attractive forces, weak intermolecular. The type of solid for silicon dioxide, this is one of the 2 exceptions. The other one, remember, is carbon. So this one here is extended covalent. And we remember with the extended covalent, these things are not molecules, they are atoms. Silicon and oxygen atoms. And they bond together with covalent bonds in one large molecule. So the only reason that the carbon dioxide are molecules is they are discrete, independent molecules. This is very strong covalent bonds. Bond. Okay, so often, I've got 3 answers here that we're going to go over. Let's put this in blue. So the way that we answer these questions is very similar. Okay, let's go down a bit and see if I can get this in. Okay, cool. Right, so it says here silicon dioxide has a melting point of 1710. Okay, that gives us a wee bit of a clue that this silicon dioxide is going to be something with very strong bonds. Carbon dioxide has a melting point of 57 degrees. Justify the statements in terms of the particle structure and bonding for both. Okay, so what we do first is we talk about the particles and the bonding for, and we'll start with the silicon dioxide. So we would say, well, let's say what type of molecule it is. So SiO2 is a covalent solid held together by, now we're going to say very strong here because this is a very high melting point, very strong covalent bonds between the silicon and oxygen. Let's just do an O here, atoms. Okay, so we've said, hey, this is, and we always start off with the same statement. We say, we're summarizing what's in the table, really. We could say that they are held together in a regular 3D lattice. That's really good. I don't necessarily need it for this one because all I'm going to do is say, because they have very strong bonds, because the bonds are very strong, only, strong, a lot of energy. Now we're going to use the word energy here. Whenever you talk about temperature, it's energy. A lot of energy is required to break them so the melting point is high. Okay, I'm just going to see if I can get rid of this chat that seems to be in the middle of the screen. So, it doesn't seem to be getting rid of it. It's weird. Attach. Anyway, let's go on and see if I can write the next bit. So now we're going to talk about carbon dioxide. However, as CO2 is a molecular solid, where the CO2 molecules are held together by weak attractions, held together by weak intermolecular attractions. The only a small amount of energy is needed to break these. So it has a low melting point. Right. That's fine there. Let's have a look. Okay, let's go down to the next bit. Copper sulfate. Okay, so the next one says copper sulfate will dissolve in water, but copper metal will not. Justify this statement. So we're going to talk about two different things again. One, why one of them does dissolve in water, and the second, why the other one doesn't. Now for this one here, and this will be a common one, what we actually want to do is possibly draw the structure of it, right? Because we're going to draw a wee diagram. So I would start by drawing lots of wee circles, yeah, here, and I'm going to draw a regular lattice really quickly. And what I'm going to do here is I'm just going to, instead of labeling these ions, I'm just going to label them as plus minus. Okay, and they're actually not plus and minus. They are 2 plus and 2 minus. But this is going to make it easier for our explanation, right? Okay, so, and then I'm going to draw a water molecule, right? Now what we have to remember about a water molecule is a water molecule looks like this. It has an oxygen and it has 2 hydrogens. Here they are like this. And we have one side of the molecule that is slightly negative and one side that let's get rid of that one there. One side that is slightly positive, right? So I'm just going to label this as a water molecule. And let's just label these two as this one here is a Cu2 plus ion, and this one here is a SO4 2 minus ion. Okay, so what we do is we draw the water molecule, right, next to this one here like this. And I'm just going to draw a wee attraction here. And I'm going to explain this. So I'm going to say the attraction that the polar, because this having a positive and negative side to it makes the water molecule polar, so the polar water molecules have for the ions are stronger. Now we're going to write something specific here, or as strong right? So you can say it this way: stronger or as strong as the oppositely charged ions, or the negative and positive ions, oppositely charged ions have for each other in the lattice. So it will dissolve. I'm just going to put in brackets here because you might add this, but the positive pole of the water molecule is attracted to the negative ion. The positive pole is the delta plus, is attracted to the negative ion, and you could say and vice versa. I'm not going to do that. This is pretty clear from this. And then now we're going to say why the copper doesn't. So we're going to say that so what I haven't done here actually which maybe I should have done at the start, is to say that copper sulfate is an ionic solid. Positive and negative ions are arranged in a regular 3D lattice. And held together by strong ionic bonds. I know that's a bit messy, but anyway, so I've put, look, and that's okay in the exam. You can go back and write something if you missed it. You can put an asterisk and you can put it down lower later, right? So the next one that we'd have to say is, okay, copper solid is made up of Cu atoms and delocalized electrons. It is held together by strong metallic bonds. Strong non-directional. Now let's say not, instead of non, we'll put multi-directional. You can use either. Metallic bonds. Metallic bonds between the electrons and the copper nuclei. Cool. The water does not. The attractions between the copper and the electrons are stronger than the attractions between. Wait, let's push this up. Okay. The attractions between the Cu and electrons are stronger than the attractions. That may form, that can form between water and the Cu atoms. So it will not dissolve. Okay, so in summary, basically, if the water or any other substance is attracted to the particles more strongly than the particles are attracted to each other, it dissolves. If the water or any other liquid substance doesn't form strong attractions and the particles have stronger attractions within their own solid, it won't dissolve. And that's the basis to how we explain this one. Okay, I'm going to go down and do the last one. Okay, and the last one is we have to say why copper sulfate is malleable and why copper solid bends. And the best way to do that is to actually draw the for copper sulfate, you want to draw the lattice again, right? And again we can just draw a general diagram. So the general diagram is remember we had these positive and negative, we're just going to draw a 4x4 lattice here, and we're going to alternate the positive and the negative ions, right? Negative, positive, negative, negative, positive. Okay, and then what we're going to draw is we're going to draw the force being applied. Sorry, that one's a negative, that one's a positive, that's a negative, negative, positive. So I'm going to draw a force here, so I'm going to write force, and then what I'm going to do is, remember, we're going to draw these, the line on the left. Okay, so this is positive, negative, negative, positive, positive, negative, negative, positive, and then we're going to draw it being part of it being shifted, right? So like this, and we're going to show, because the picture is really strong here, we're going to show that this positive is shifted down, and this the whole line has been shifted down. And so we're going to draw something like that. And I'm just going to draw an arrow and to show that these have been pushed apart. Okay, so and then we want to explain this. So we would say, you know what, I didn't notice that, but I've been drawing them and they have been too high. So here we go here. All right, so we've got that happening here. So I'm going to say when is it forces applied, or I don't really have to explain about copper sulfate being an ionic lattice because I did it in the previous question. So in this case, I'm going to go straight to explaining what's happening here. So when a force is applied to the solid, but if they hadn't asked me about it beforehand, I would explain that this is an ionic lattice made up of copper and sulfate ions arranged alternating arrangement of copper and sulfur ions would be a better way of doing it. So when a force is applied to the, I'm just going to write ionic solid so they know that I know it. the lattice shifts, may shift, and positive to positive to how am I going to draw this? Wait a sec. Positive ions end up next to positive ions. Ions and negative next to negative. Next to negative. As like charges repel, the lattice fractures is forced apart. Let's just say is forced apart. So that's the first part. So I've explained here how it is that this lattice has fractured. Now you might remember again, if you had to, you would write down this is an ionic solid. It is made up of alternating copper and sulfate ions arranged in a regular 3D lattice with strong ionic bonds between the copper and sulfate ions. But I wrote that before, so I'm not going to write that again. We're going to say as the, for the next one, as the copper solid has as we're going to say multi-directional, let's say strong multi-directional, that's fine, strong multi-directional bonds between, let's say metallic, between the delocalized electrons and the, let me just put that up a bit, and the nuclei of the copper atoms. New bonds are formed as old ones diminish when a force, so we're hitting this with a force again, when a force moves atoms in the lattice. A force moves the atoms in the lattice. And that is kind of the end and all I have for you here. Now, the question is, the question will be for you and to say something in the chat if you found this helpful. The other thing I need to do is to find out why it is that the chat is sitting in the middle of the screen. And that I have no idea about. I am going to... No, that's not going to work. Studio mode. Chat. The chat is still there or not? That is really weird. Are you able to drag it? No, because like, I can't see it. So it's on a program called Prism Live, and it just seems to be there. And I will have to work out how it works. So if I do this again, it's not going to be there. Does anyone have any questions? Does anyone have any suggestions? Was this helpful? Would you like me to go over anything else at another time? You can just let me know about that. Just write something in the chat, I guess. Let me see. Okay, I'm going to look to do something on the next Sunday, and what I'll try and do is just make it half an hour so it's not too cumbersome. And what I want you to do is just message me or let me know what you would like me to go over. Which ones do basically I'll just put some questions on and go over how I might do it. How do you tell the difference between a molecule and an atom? Okay, that's a good one. Just let me just say about that. Now the problem is with a molecule and an atom. Okay, I'm going to put that there and let's do this. So an atom is, so this is an atom, this is an atom, this is an atom. So an atom is always just one. Okay, so it's one symbol. That's what an atom is one symbol. And then a molecule is when you have more than two of an atom. So it could be something like H2O. I have two hydrogens and one oxygen. Now, you see what we can have is helium is an individual particle, but it's an atom as well, right? Because it only has one I'm going to use the word atom in it, right? It's only got one atom in it. But if you have more than one atom in something, we call it a molecule. But you can also say this molecule here, water, contains two hydrogen atoms and one O atom. Yeah, we can go over some organic chemistry too. The trick is the extended covalent ones are always lots of atoms joined to other atoms like this. So if this was diamond, this is how diamond would look, right? Strong covalent bonds. So it doesn't have individual molecules. But if I was to draw water for you, it would look like this. It would be H2O. There would be one particle, not a big giant particle, not like this one, a big giant lattice. There would be just one smaller particle, and this, because it is smaller, is called a molecule, and sometimes it's called a discrete molecule. Anyway, that's kind of what that is. I'm going to say goodbye, and I will... Can you see what I'm drawing? You can... Oh, right. Yeah. And you know, the other thing that's a wee bit of a drag here is that there's a wee bit of a lag time here for this, which is kind of interesting. So I'll quickly just go over this again. Just so we have atoms are the things on the left. Okay, so these are atoms. We have one carbon atom, a hydrogen atom, and a helium atom. And if they were particles just by themselves, they would look like that. But we can also have atoms can be part of a molecule. H2O is a molecule. It's an individual particle, but it actually has 3 atoms in it. When we talk about molecular solids, they are discrete molecules. Okay, so they're individual molecules. Even though they contain atoms, we just need to say that this has an H2O molecule. When we have this one here, which is the diamond again, extended covalent network it can be called. It is one huge molecule made up of millions and billions of atoms. But we can't write that down. So what we say is it's actually a covalent network where the individual atoms, these individual atoms, are bonded to each other individual atom by covalent bonds. Hopefully you can see the drawing now. Okay, I'm going to stop this now and I'm going to see if I can work out why the chats are doing